right, so I'm going to go over the light waves notebook. So page 1 is asking, is light an example of a mechanical wave or a electromagnetic wave? And then the big part of this is the why. So let's start with mechanical waves. So an example of a mechanical wave was when we were studying sound or ocean waves. And then if we think back to there, if we look back at your sound wave notebooks, it'll say that sound waves are created from vibrations, and that because they are vibrations, they need a medium or something there to vibrate. So a solid, liquid, or gas. So they physically need something there to vibrate. It's mechanical. It needs to physically vibrate for it to then travel and move. Electromagnetic waves don't need that material to move. And that's because light, which is electromagnetic, is made up of particles. So light waves are electromagnetic because they are made up of particles. Therefore, they do not need a medium to travel or move. And then on top of that, because they are also particles, they have a physical thing that makes them up. So it's not like vibrations where it's something being shaked, vibrator is something that then causes those vibrations to cause that sound. Light can then be created, and then it's a thing that's there that then can move through space. Unlike sound, when we learn sound can't move through space because there's nothing there for it to travel on, light can move through space, and that's why the sunlight is able to get to us from the sun to Earth. This one will be a big one for the test. Page 2 is why does light appear white? And if you go back to our lab 4, where we did the different dials to see if we could make all those different colors, light gets its color because it's a mixture of all light, of all colors. And that's also why when we have like rainbows being made, it's white light being refracted, meaning it's white light being refracted by water and splitting apart into all of its different colors. And that's why we're able to see a rainbow. Now, the bottom question is, which color would absorb the most light or energy/heat, black or white? White is the most reflectant, meaning, so if you have a white object like this receipt I have, the white light comes off of it and all of that light bounces back to your eye. However, if something's really dark or black, all the light is being absorbed, all the colors, all the white light. That's also why darker things in the summer get a lot hotter than the lighter things, because it's absorbing more light than the white. All right, and this is how we see color. So blank light is created by the sun or light bulbs and hits an object. The sun creates white light. The object blanks most of the wavelengths or colors, but will blank at least one color to the human eye. Absorb, reflect, and the object appears to be that reflected color. So what this means is that, again, I got this purple sticky note, white light. So right now my light bulb is making white light that comes and hits the sticky note. Every color but the pink or purple, whichever color you want to call this, is absorbed, but then that remaining pink or purple is then bounces off to my eye. It reflects back off of it So the color that you see of everything around you, except maybe black, because black absorbs all colors, every other color from red to purple that you see, or brown, that you see, is created because that color is being reflected back at your eye. Now for this part, we're going to talk about this more when we do our CER about lasers. And this is talking about how different colors have different frequencies. And frequencies meaning the number of waves, which then correlates to the more waves you have, the more energy you'll have, the faster the wave will be because you're putting more energy into it, so it's going to speed up. And also, as you put more waves in, you make the wavelength a lot smaller because you have to jam more and more waves in there. So you get a lot of energy. It's kind of like if you think about it at a beach. Which beach is going to be crazier? The one that has a few waves or the one that has wave after wave after wave? The one that has tons of waves crashing on that beach. And how it goes is that, and it goes in the order of the rainbow. It goes from lowest to medium to highest. And what you'll see in that CER that we do is that the red, like laser pointers, it's really bright, but they don't have a lot of energy behind them. And then as the laser gets darker in color and gets closer to purple, that's when it starts to actually be able to burn through stuff. And we'll see that when we do our CER. All right, we're going to do this part now too, which we're going to match up the scenarios to the different properties of light. So transmittance means that light goes through the object. Refraction means that light goes through, but then when it comes out the other side of the object, it gets bent, or it can be split, or it warps the light, therefore causing images to look weird, or causing the light to do weird stuff, the light to change. Reflection is just what it sounds like. You have a mirror, the light bounces off of it. That's also why we're able to see our reflection, is because the light is bouncing off of it to your eye, so you're seeing that. And then absorption, which is the light is being completely absorbed by that object. So sunlight is shining through a window, transmits, or if you put it a little bit in refraction too, I'm fine with that. But transmittance starts with a T, light shining through. If it ever goes through and out the other side, that's an example of transmittance. But if you also are thinking refraction too, you can put that down there. The glass will probably refract it a bit. The creating of a rainbow, we talked about that a little bit earlier in one of the slides. That is refraction. One, that's how rainbows get their arc, because the light is being bent. But also, the white light is able to then turn into all those different colors because one, it gets bent, but two, as the light hits the water droplets, it breaks the light apart into all of its different colors, the red, orange, yellow, green, and blue. Kind of like how we saw up here. It breaks them all down into the different colors and then bends them all. So it's kind of two examples of refraction. It's what we call scattering, which is breaking it apart and scattering the light, and also bending it into that arch. Object shape or size being changed underwater, again, creating an illusion, making, if you put like a pencil in the water, it'll look bigger than it does outside of the water. That's an example of refraction. If you ever see something talking about how it's warping an image, it's usually always refraction. Seeing your image on the surface of the water, again, you're seeing your reflection. That is reflection. Black pavement getting hot in the summer, that's absorption, because that black pavement is absorbing all the light, all the color. The same would go for black paint. And then white. White is unique because it reflects all light. So if you ever go out at just when if it's ever like the ground is covered in snow and it's a bright sunny day and you go outside, you always feel like you're getting blinded and it's extra bright out because it is, because all that snow is reflecting the light back at you. And that's also why like snowboarders and skiers have to wear, especially at the Olympics, have to wear a lot of sunscreen because all that sunlight is being reflected back at them. It's kind of like just sticking a mirror on you the whole time and letting the sun just bounce off that directly at you. So that would be reflection. Awesome. So follow along through this. You can then fill out the rest of your notebook. And again, this notebook's going to be really, really useful on your test that's going to be coming up. So look this over, and yeah,